Welcome everyone. So this is our 61st live stream geometry. We have 2 people here with us so far, and I'm going to continue with more problems from the Saudi Arabia team selection test. So I've been doing it for the past couple sessions, and there's just a lot of problems there. I don't know if this is going to be the last one or if I'm still going to be able to do like 1 or 2 more. So if you'd like to join sessions in the future, feel free to email me at mgreenb801@gmail.com. The sessions are on Sundays at 8 a.m. US Central Time. And I see we just had someone else join us. So I'm going to go share my screen. Hold on just a second. All right. Are you all able to see it? So
Yes.
Okay. So here's the first problem. So we have a triangle ABC, and it's inscribed in a circle O. All right. We're a circle centered at O. I feel like GeoGebra starts out a little slower and then gets faster. Yeah, like right now it's pretty fast. Then we draw the 2 tangents at B and C. So your usual symmedian configuration. Let me try to make some room. So like that. And I guess if I want B and C to intersect not too far away, then I think I should make angle A more like almost obtuse. Or no, actually more narrow. So something like that. Let me shrink the figure a little bit. There we go. All right. Then we draw the bisector of angle BAC. And it intersects the circle with center P and radius PB. So here's point P. And this circle with center P and radius PB, it's used in the proof of the main symmedian theorem. So, or I know of a proof of that uses this circle. So this will be point E. And M and N are the midpoints of arcs BC and BAC. So I could draw both of them at once using this. And obviously these meet at the midpoint of arc BC right here. So this is M. This is N. And then we draw the circle with diameter BC. And it intersects segment EN at F. And it passes through that point too, but it intersects EN at F. And we want to show that the orthocenter of EFM lies on BC. All right, so let me hide some of the extra stuff. Right, so we have this. Was that everything? I think that might be everything. So, is it true? I think. Oops. Oh yeah, no, these don't concur. Yeah, I was wondering, it looked like it, but yeah, they don't necessarily concur. So I'm just going to erase MN. Okay, so we want the orthocenter of EFM. So this kind of narrow triangle. Maybe it's worth drawing it. So it's way over here, but it lies on BC. It's interesting. Whenever I have a point that's like way out here, I think about like using, I don't know, maybe NA and G. I don't think NA and G are collinear. But I'm going to draw GF and GM. Just because, oh, so it looks like this passes through that point. Let's see. Yeah, it looks like those all concur. Okay. So if you take the perpendicular from F to AM, yeah, basically, yeah, it intersects. Well, yeah, that kind of makes sense because actually, no, I'm not so sure. So if this is a right angle, that means if we extended it to hit the circle, it would meet it at the antipode of F. Let's see. I wonder if this point is special right here. Oops, sorry. Does that always pass through it? Huh, interesting. So yeah, so basically, I mean, that would mean like FHIM is cyclic.
Also, another special point, there is a GE intersects FM at the circle.
Okay, hold on one sec. GE intersects FM. That's interesting. All right. Okay, so now it's like looking a little more, because yeah, if we can show FHEJ is cyclic and EJIM is cyclic, yeah, maybe that would be a step forward. All right, let's see. Yeah, is there anything special about point E? So yeah, I'm just going to draw this segment right here. Yeah, what can we do with the circle P? Can we use that this is a symmedian? So I wonder, yeah, I don't know if those points are going to help. We have to use that PE is equal to PB is equal to PC. Actually, I can draw this all the way. Almost feels a little like poles and polars. So we want to show G lies on the polar of P. What's the polar of G? Okay, so H, it looks like H lies on the polar of G. And maybe this point there does too. It looks like there's a point right here. So basically, H, K, and P are collinear, it looks like. There's a lot going on here.
Can you just check it again?
H, K, and P.
Yeah.
Yes. Yeah, they're oh no, actually, I think you're right. Yeah, they're not. Good catch. I got tricked. So yeah, let me get rid of point K then. But let's see. If I move, wait. Now it looks like it's kind of true. This makes it look, I'm not sure what just happened. Oh, because this doesn't always pass through H. Like the H doesn't lie on the polar necessarily, that's why. But this point looks, yeah, this point does. What if I draw this? One sec, I'll be right back. All right, thanks for waiting. So yeah, we found a lot about this configuration. Let's see.
So we basically want to find prove actually some 90-degree angles. Like we want to prove that EHF is 90 degrees.
Yeah. Okay. Yeah. So we want to prove that EHF is 90.
But that would be equivalent to showing that HF is parallel to AM.
Or perpendicular to AM.
Parallel.
Oh, HF and AN. Oh, AN. Okay. Interesting. Yeah.
I also found that HJDM looks cyclic.
Oh, really? HJDM?
And also HEDN.
Oh, because, well, that would have, if these really did concur at G, yeah, then HJDM would have to be cyclic because these are all right angles, right? GHM, GJM, and GDM. But what was the other one you mentioned?
EDNH.
Oh, GDMH?
EDNH. No. Yes.
Oh, EDNH. Interesting. Okay. How do we prove that one? Well, I guess we could try doing power of a point from M, right? Like we'd want to show that MB times MN, that's MB squared. And we want to show that that's ME times MH. Which is the same as, so yeah, we want to show angle EBM is angle BHM.
Is it true that E is the homothetic center of ABC and the circle with diameter BC?
Oh, that's a good question. Well, no, so the homothetic center, I think would be the intersection of the common tangents, right? You mean these two circles? The circle ABC and the circle with diameter BC?
What is the internal homothetic center?
Oh, the internal, but shouldn't it be on, like, by symmetry, shouldn't it lie on the perpendicular bisector of BC? Because these two circles both pass through BC, right? So yeah, can we show that ME times MH is MB squared? What if let me just try this. I wonder if, so this point kind of looks like the incenter right here. So this, this is looking a little bit like the Sharky Devil configuration because, let's see, so this point, oh no, the incenter would be this point, but it looks like this point also lies on this circle. Or so yeah, it's like MK equals MB equals MC. Yeah, it feels like it might be worth redefining a couple things in the figure. Just thinking about the best way to do it. Because E, we have to use that E, so E lies on the circle. So does that give us any angles? Maybe that could give us some angles that will help us show that this is cyclic right here. So yeah, because like I said, we wanted to, if we can show that angle BHM is EBM, that solves it. But EBM is EBC plus CBM. And EBC is it's half of EPC. Let's see. Yeah, E is just defined in a weird way. So yeah, we could try to calculate angle BEC in terms of BAC. I wonder if BEC is twice BAC or I'm not sure. But yeah, it would just be a calculation. So this, okay, so I think BEC is 90 plus angle A. Just did the calculation in my head, but yeah, it should be. So that would mean this should be like 148.61. Yeah. Can we use that in any way? Okay, so angle BHC is 90 and BFC is 90. So that gives us some like isogonal lines. So basically, HB and HM are isogonal, I think. Yeah. And I wonder, yeah. I wonder, let's check this out. So like I wonder if I draw the tangents from T to the circle. Like, oh, is GA tangent to the circle? Oh, I think once we know that, I think things might get a little easier. So yeah, it looks like GA is tangent to the circle, I think at least. And it also looks like this median point, it looks like that is the point of tangency. So,
I don't think that the GA is tangent.
Oh, you don't think so? Okay. Yeah, I think you're right. And yeah, this doesn't look tangent either. Okay. Or yeah, it's not tangent at the intersection point. Okay. Yeah, this is interesting. A lot going on in this diagram. Yeah, E is just defined in a difficult way. I wonder. So yeah, this would be maybe I don't know if it would help if I drew more circles. Get this circle. That. Let's see. Yeah, this looks like a hard one. You guys want to move on to the next problem and come back to this?
Yes.
Okay. So this one is 2 parts. So we have a triangle and then we draw the in-center. D, E, and F, and then I is the center. So we have the line through A parallel to BC. And then we see where it cuts. Oh, this looks familiar, this kind of idea. So I think we get a lot of isosceles triangles, right? So we see where it cuts DE and DF at M and N. So yeah, AEM is isosceles and AFN is isosceles. And so because of that, we have that A is the circumcenter of NFEM, that cyclic quadrilateral. So I'm just going to draw that before I even finish the rest. So we have that circle. The circumcircle of BMN cuts the in circle at L. So this is point L here. And K is the intersection of NE and MF. I'm just going to draw segments. Oops. Okay, so we have like the cyclic quadrilateral NMEF. And this is K, and it looks like it lies on the in circle.
The part A we already proved.
What was it in like a previous session?
No, literally, after proving that A is the center of that circle, it is then we can see that K is the orthocenter.
Oh yeah. So yeah, K is the orthocenter, and so then it's an easy. It's trivial. And then A, K, and L are collinear. Well, we know that D, I, and K are collinear, right? Because DEK is 90 degrees. And let's see. If we can show angle ALD is 90 degrees, that would solve it. Obviously, if you drew that line, it would meet it at the touch point of the X circle.
L is DQ point, so AKL are collinear.
L is the McKell point, or what did you say?
L is DQ point.
The
Q
Q
point.
point. Ah. So yeah, it's the Q point of triangle DMN. Oh, and so it's collinear with K and A, because A is the midpoint of MN. Okay, that was very easy. All right. We solved the problem before I even made the diagram nicer.
Oh, I have actually another solution to this.
Oh yeah?
It is actually really easy to use power ratio lemma here.
Oh really? Interesting. How do you do it?
So we extend the dk to meet m.
MN?
Yes.
Sorry.
And then we want to prove that AGLD is cyclic.
Okay.
And for that, we will use power ratio lemma. So power of A with respect to DLMN, that is equal to AM times AN, or rather AM squared. And that power over power with respect to incircle, that is AE squared.
Okay.
But that is actually equal to 1.
So yeah, the ratio of the powers is 1.
And then power of G with respect to DLMN is GM times GN. And with respect to incircle, it is GK times GD.
And they're the same thing. Yeah. Interesting. So I like that uses the power ratio lemma, but I think I'm going to write a GEO King solution just because it's shorter, but I kind of like that. So it's interesting. All right. So yeah, let me just type it up quickly. So we have AN equals AF equals AE equals AM. So that means that NFEM is cyclic with center A. And so since angle NEM and NFM are 90 from that, that means that K is the circumcenter of DMF. Or DMN. That's part A.
The orthocenter.
Oh, sorry, orthocenter. And then, yeah, it's well known that, so I'll just say L is the Q point, QUEUE. DMN. So yeah, it's a well-known fact that the Q point, the orthocenter, and the midpoint of the side are collinear. So all right. And yeah, the power ratio lemma 1 is interesting too. I like that. All right, so I'm going to move on to the next problem. Let's see how hard this one is. So we have a triangle ABC and a circle O, and P is any point. So that's pretty flexible. D is the point, so that AD is perpendicular to AP. Just trying to move P so it doesn't look like it's on altitude. That's weird. The only thing it says about point P, oh, there's one more, P is used there too. Okay. So this is a point D, and then CD intersects the perpendicular bisector BC. All right, looks like Hoy just joined. So we draw the perpendicular bisector of BC and let's see, it meets that at, hey Nguyen, thanks for joining us. So this is point M. And then AD cuts the line through B and perpendicular to BP. Okay, so we want to draw this perpendicular. And let's see where it cuts AD. So that's Q. And then N is a reflection of Q over M. And we want to show that CN is perpendicular to CP. This is very random, this problem, but all right. So let me first draw CN and CP. We want to show that's a right angle. Whoops. QA and D, and then, yeah, we just draw QB. So P can be any point. Yeah, whatever point P is, we want to show that this is like a right angle, angle NCP. So we know that this is a right angle. So yeah, there's almost a kind of symmetry, right? Oops, sorry. We know that this is a right angle, and whoops, and we want to prove that the other one's a right angle. So yeah, given that one of them is a right angle, prove that the other one's a right angle. I think I accidentally hid the perpendicular. Yeah, so M lies on the perpendicular bisector. So I think we can kind of rewrite this problem. We can say, let me see. Yeah, we want to use that. This is so. This is also a right angle. So yeah, it's very symmetric. We have 3 right angles like that. What if I see where this meets the circle? And where this meets the circle? So we've got this point and that point. Maybe MF and P are collinear. Interesting. Oh, but no, I don't think that's actually true. I think that's just coincidence. Yeah. All right, let me delete these 2. So yeah, this is cyclic. Oh, yeah, no, I was gonna say QP and O can't be collinear.
Perimeter is BM parallel to ID.
DN.
BM.
Oh, sorry, BM. I don't think so. Yeah, these aren't parallel. Yeah. I wonder, like, what if we let DN intersect the circle at a point? I'm trying to like use symmetry somehow. I don't think that does much. So yeah, like what if we try to make like the pedal circle? So like what if we draw this, this, and this, and they make a triangle. And then those are the 3 feet of the perpendicular from P. Maybe like there's an isogonal conjugate of P in that triangle. Oh, whoops. So O and P, I think, are orthogonal conjugates, right? Or maybe.
The reflection of P across O is the isogonal conjugate of P.
Okay.
In the big triangle. Like,
Yeah, and the big.
the triangle formed by the.
Yeah. If I draw this. So yeah, maybe we want to use that. If M is the midpoint of Qn and F is the midpoint of Qp, maybe we could use that somehow, like Fm is parallel to Pn. I don't know. I'm going to delete P prime. Let's see. Is there another point on this circle? I don't think so. Oh, but it looks like these concur on this line, dn. So maybe that's useful. Yeah. I guess that would be obvious if the problem were true, right? But still, we could name this point. So we want to show that CPGN is cyclic. Just tricky. How do we take advantage of the symmetry? Yeah, what's the best way? Okay, so we want to show PGMC is cyclic. Um, but yeah, is there another point on that circle? I don't think we saw one. Doesn't look like it. Yeah, I really want to draw this point. I just don't know what it does. Why?
Can you extend the line QB, ME, and NC?
A QB and MC? Yeah.
QB, ME, and NC. Yeah,
Oh, yeah. Let's see if they concur.
I'm not sure.
I don't think they do because there's so much like flexibility. Like, yeah, they don't concur. But okay, Khan is joining us. All right. Thanks for joining, Khan. So yeah, we have an interesting problem here. So yeah, we start with any point P. So P can be any point inside triangle ABC. And then we draw the perpendiculars to PB and PA. And they meet at Q, and this one meets the circle at D. And then CD intersects the perpendicular bisector of BC at M, and then we reflect Q over M, and we want to show angle, we want to show CN is perpendicular to CP. So yeah, let me see if I can draw it so that we can see the intersection of these lines. So I'm gonna get rid of this one, but like the other two, maybe if I move point P, yeah, that makes it a little better. Okay, so yeah, I just want to see that point. Okay, so I draw this point right here. So then GBC is like the pedal, or we want to show that that's the pedal circle of P. I wonder if it passed, let's see. Maybe GBCM is cyclic. Ah, I think that might be the key. Is that true though? Is GBCM really cyclic? Yeah, okay. I think that's going to help a lot. So yeah, we don't even really need to intersect these to see that. We just want to show GBCM as cyclic. me see. I still want to see that point H. Oops.
You can angle trace the GBMC.
Is cyclic?
Yes.
Okay. Oh, because angle MCB is the same. Let's see. Yeah, because you can calculate angle MBC or
MCB is QAB.
oops, sorry. My GeoGebra is going crazy. MCB is QAB.
And that is equal to QGB.
Okay. Okay, so if we know that that's cyclic, then
Maybe, sorry.
oh no, sorry, go on.
Maybe P is the in-center of triangle GBC.
The in-center. Let's see. I think you're right. Let's see. Oh, I think it's a little bit different. Let's see. Yeah, not necessarily. So, but it almost looks like it lies on the angle bisector at least. Let me move things around. Yeah, because like this is not the in-center of GBC. But it still looks like it lies on the angle bisector. So that might still tell us something. So let me draw the center of that circle. It's going to lie on this, obviously. And then if we reflect P over I, that point PM is perpendicular to QN. So yeah, those are orthogonal conjugates.
you can prove that P prime O is perpendicular to Qn, Qn, we will finish this problem.
If I can prove that P prime M is perpendicular to Qn, or P prime O.
P prime O. Sorry, P prime M. P prime M.
Oh, P prime M, yeah. Yeah, if I can show that, that would solve it.
I think it's quite obvious, right? That P prime M is perpendicular to Qn.
Why?
It is clear that P prime M is perpendicular to Qn.
Why is it clear that P prime M is perpendicular to Qn?
If you call the midpoint of GM.
Okay.
And you have P. I think that it's quite obvious, but I can explain clearly.
Oh, but do we know I is this? Oh, because I is the center of that circle. That's why. Okay, yeah, no, it's obvious. You're right. Yeah. Okay, so yes. Okay, so I'm going to start writing up the solution.
So when we have P prime M is perpendicular to Qn, so that angle P prime Qn is equal to angle P prime NQ. So that because P prime is the orthogonal conjugate of P, so P prime Qn equal to P prime NQ is equal to angle PQH equal to angle PNH, and so that angle PGC equal to angle PNC, so that GNCC is cyclic.
So I think you did the whole. I think we can just, so isogonal conjugates have the same pedal circle, right? So if P prime M is perpendicular to Qn, then so basically we know that B and G lie on the pedal circle of point P, and so if we can show that M also lies on that circle, then Stefan proved before that BGMC is cyclic. So if we could show that M lies on it, then that would mean PC has to be perpendicular. But yeah, so I think if we use the fact that isogonal conjugates have the same pedal circle, we can avoid like an angle chase. So I'm gonna type this up. So I define P prime as a reflection of P over the center of this circle BGMC. Okay, so let me first start writing this up. So we have so let's see, we have angle MCB equals angle DCB, which is equal to angle QAB, which is QPB. Is that the right angle we want? QAB, which is QGB. And so BGMC is cyclic. And then we could say let I be the center of that circle. So obviously I lies on OE by symmetry. Or we could say I lies on ME by symmetry. Or I could say OE. I don't even need to, or OM. I don't really need to define point E if I don't want. So then let P prime be the reflection of P over I. Okay, so maybe this is harder than I thought actually. So give me just a moment. So yeah, okay. So basically P, oh, but we don't know yet. Yeah, I'm actually, I think there might be another step because it's not hard to show. So yeah, so we know that P prime M is perpendicular to QN, right? So yeah, we don't know yet that P prime is the isogonal conjugate because we don't know that BGC really is the pedal circle. That's where I got confused. I kept thinking like we know that P prime is the isogonal conjugate, but we don't really, right? Like we don't know yet that P prime or Nguyen. Did you think you had a solution, a full solution to this?
Yeah, at first I think that BGC is pedal circle of P. So it's a mistake.
Yeah, I think there's still one more step to prove it because like we know that these are perpendicular, but we don't know yet that this one's perpendicular, right? So we can't say that this really is the pedal circle. We have to use that M is the midpoint of QN. We have to use that somewhere in the proof. And I don't think we've used it yet. So let's see. If yeah, where do we use that QM is equal to QN? So then PN is parallel to FM. I wonder if it's worth, we want to use that QM is equal to MN. Is there anything special about these points? So maybe we could prove that PK is perpendicular to BH, or PL is perpendicular to HN. Yeah. Oh, wait a sec. See who's on. Okay, so we have both Con and Wen on. Can we make parallelograms somehow? Because QM is equal to MN. It's the center of that circle. No, that doesn't do much. Let's see. Take a perpendicular. Oh, is E the orthocenter of QMN? I doubt it. Doesn't look like, yeah. So BE equals EC and QM is equal to MN. Can we use the Gauss line somehow? I don't think so. One sec, I'll be right back. All right, let's see. Let me check the chat. Thanks for waiting. Yeah, we can move on to the next problem. Whoops. Yeah, we're about halfway through the session.